A pizza parlor charges $1 for each vegetable topping and $2 for each meat topping. You want at least 5 toppings on your pizza. You have $10 to spend on toppings. How many of each type of topping can you get on your pizza? So what we're going to do here is set up a system of inequalities, solve that system of inequalities, see where those two inequalities overlap, and that's going to give us the amount of toppings that you can have on your pizza given these restraints. It's $1 for vegetable topping, $2 for meat topping. Altogether, that needs to be less than or equal to this $10. Also, the number of toppings, it says you want at least 5 toppings on your pizza, so the number of toppings needs to be greater than or equal to 5. So we're going to let a variable represent each type of topping. It doesn't matter what variable you use. I'm going to let x equal the number of vegetable toppings, and then y would equal the number of meat toppings. So the two inequalities we're going to set up for this system would be 1 times x plus 2 times y. That is less than or equal to 10. X is the number of vegetable toppings, y is the number of meat toppings. So x plus 2y is less than or equal to 10. For the second inequality, the number of toppings needs to be greater than or equal to 5. So if you take the number of vegetable toppings plus the number of meat toppings, x plus y, that needs to be greater than or equal to 5. So those are the two inequalities. We're going to solve that system. And where they overlap, that is the solution set. So we're going to graph each inequality that x plus 2y is less than or equal to 10. To graph that, you're graphing the boundary line, x plus 2y is equal to 10. I'm going to get that in slope-intercept form, though. Subtract x from each side. You have 2y is less than or equal to negative x plus 10. Divide each side by 2. Y would be less than or equal to negative 1/2 x plus 5. So the boundary line is y equals negative 1/2 x plus 5. To graph that, put a point at 5 on the y-axis. Then from there, the slope is negative 1/2. Go down 1 to the right 2, put another point, and draw a solid line through those 2 points. And then everything below that is shaded because you have the less than sign. So solid line because you have less than or equal to sign, shaded below because of that less than or equal to sign. Graph the second inequality, x plus y is greater than or equal to 5. Get that in slope-intercept form. Subtract x from each side. You have y is greater than or equal to negative x plus 5. So the boundary line is y equals negative x plus 5. To graph that, put a point at 5 on the y-axis. And then from there, the slope is negative 1. So from that point at 5 on the y-axis, go down 1 to the right 1, put another point, and then draw a solid line through those 2 points. Solid line because you have the equal to sign attached to that inequality sign. Shade everything above that line because you have a greater than sign. So greater than or equal to, it's a solid line shaded above. That is the graph of the second inequality. But on paper, you want these right on top of one another. That shows the overlap. So if you stack those two inequalities, one right on top of the other, you can see where the overlap is. But you have to keep in mind here, we're not talking about negative toppings. So for x being negative, that's out of it, and x doesn't turn negative as far as the overlap is concerned. But for y being negative, that's out of the picture as well because the number of meat toppings cannot be negative. So y is the meat toppings, x is the vegetable toppings. All of these whole number coordinates that are positive, those create the combination of toppings that you can have. So for example, with x being the number of vegetable toppings, y being the number of meat toppings, you could have up here at the y-intercept 5 meat toppings and 0 vegetable toppings, where x is 0 and y is 5. And if you go on further down, you could have 4 meat toppings, where y is 4, the number of meat toppings is 4, and then with that, you could have 1 or 2 vegetable toppings. So where y is 4, x could be 1 or 2. Also, you could have 3 meat toppings where y is 3. If you go up 3 on the y-axis, x could be 2, 3, or 4. In other words, you could have 2, 3, or 4 vegetable toppings. For 2 meat toppings where y is 2, go up 2 on the y-axis, x would be 3, 4, 5, or 6. So those are all the combinations that you could have of meat and vegetable toppings. You could have 1 meat topping and 4, 5, 6, 7, or 8 vegetable toppings. And then finally, where y is 0, you could have 5, 6, 7, 8, 9, or 10 vegetable toppings where x is 5, 6, 7, 8, 9, and 10. So again, we're talking about whole number coordinates here. In that overlap, we're not going down here into the negatives, even though the graph shows that it could be negative as far as the overlap goes. We're only talking about whole number positive coordinates, whole number positive combinations for the meat and vegetable toppings. So this overlap, where x and y are positive, right in here, those are all, and whole number coordinates, those are all the combinations that we could have for meat and vegetable toppings. You want to decorate a party hall with a total of at least 40 red and yellow balloons. You need a minimum of 25 yellow balloons. I'm going to right graph a system of inequalities to model this situation. So we're going to let variables represent the number of red and the number of yellow balloons. So let R equal the number of red balloons, Y would equal the number of yellow balloons. You need a total of at least 40 red and yellow balloons. So you can take R plus Y, that would be greater than or equal to 40. Also, you need a minimum of 25 yellow balloons. So Y needs to be greater than or equal to 25. So those are the two inequalities. We're going to graph those two inequalities, and where they meet, where they overlap, that will give us all the combinations of red and yellow balloons that we could have. So take that first inequality, R plus Y is greater than or equal to 40. You're going to graph that just like an X and a Y. We have an R axis and a Y axis instead of an X axis and a Y axis, R axis and Y axis. So we're going to get that in slope-intercept form, subtract R from each side. You have Y is greater than or equal to negative R plus 40. So we're graphing the boundary line Y equals negative R plus 40. Now this coordinate point is in units of 6. So put a point at 40 on the y-axis, then from there the slope is negative 1. Go down 1 to the right 1, put another point. And we're drawing a solid line through those 2 points because of the greater than or equal to sign. We're shading above that boundary line because of the greater than sign. So with the greater than or equal to sign, it's a solid line through those 2 points shaded above. Now for that second inequality, y is greater than or equal to 25, we're going to graph the boundary line y equals 25. That's a horizontal line through 25 on the y-axis. So a horizontal line through 25 on the y-axis, and we're shading above that line. Because of the greater than or equal to sign, it's a solid line through 25 on the y-axis, shaded above. Now on paper, you would put these together, one on top of the other one. I have them separated so you can see each one individually. But on paper, this is what it would look like when they are together. So the overlap here, this top section, gives us all the combinations that we could have of red and yellow balloons. A couple key points: where y is 40, r is 0. So the number of red balloons could be 0, and the number of yellow balloons could be 40. Also, where y is 25, r is 15. Remember, you need at least 40 red and yellow balloons, so you could have 25 yellow balloons and 15 red balloons. Or back up here, you could have 0 red balloons and 40 yellow balloons. So some different combinations that you could have, along with what I just said, that would be found in that overlap. Now you can't have a fractional balloon. That would be no balloon at all. But you could have 0 and 40, 0 and 41, 1 and 39, and so on. You just need at least 40 red and yellow and a minimum of 25. So again, where y is 25, r would be 15. That's a minimum of 40 red and yellow balloons. Or where y is 40, r would be 0. You might have 0 red and 40 yellow. So those whole number coordinates in that overlap give us all the combinations that we could have of red and yellow balloons. Have fun at the party. Just a quick review of graphing absolute value inequalities. If you have the absolute value inequality y is less than or equal to 3 times the absolute value of x minus 1 minus 2, remember, you can see the vertex. The vertex would have coordinates of 1 and 2. So this would be a V-shaped graph. This graph will be opening upwards. It's a V-shaped graph with a vertex of 1, negative 2. And the slope of the right branch, that number in front of the absolute value sign, is 3. So the boundary line that we're graphing is y equals 3 times the absolute value of x minus 1 minus 2. Again, the vertex is located at hk, and the slope of the right branch is the number in front of the absolute value sign, that's 3. So you put a point at 1, negative 2, that is the vertex, and then from there to get another point on the right side, the slope of the right branch is 3. So point at 1, negative 2, that's the vertex, go up 3 into the right 1, put another point. That's the slope of the right branch is 3. The slope of the left branch is -3. So from that vertex, you could go up 3 into the left 1, put a point. Those 3 points make your V-shaped graph. So draw the V-shaped graph through those 3 points. And then as far as the inequality aspect goes, you have a less than or equal to sign. So that's why it's a solid boundary, because we have the equal to sign. And then everything gets shaded below that because of the less than sign. So once again, the vertex is right there at 1, -2. The slope of the right branch is 3. And the slope of the left branch would be -3. So from that vertex, 1, -2, you could go up 3 into the right 1, up 3 into the left 1, put those 3 points down, draw a V-shaped graph through those 3 points, make it solid because you have a less than or equal to sign, and shade everything below, again, because you have the less than or equal to sign. So that is the graph of that absolute value inequality. We're going to solve this system of inequalities by graphing. Now, the first inequality, that's a linear inequality, so that'll be a line shaded above or below. The second inequality, that is an absolute value inequality, so it'll be a V-shaped graph shaded above or below. So we'll take that first inequality, y is less than -1/3 x plus 4. To graph that, you're graphing the boundary line, y equals -1/3 x plus 4. So put a point at 4 on the y-axis, then from there go down 1 to the right 3, put another point. And since we have a less than sign, we're putting a dashed line through those 2 points. And then because of the less than sign, we're shading all points below that dashed line. So that is the graph of the first inequality. Now on paper, you're stacking these one right on top of the other. I will keep them separated and then put them together in the end. For y is greater than the absolute value of 2x minus 1, that is an absolute value inequality. First thing you need to do is factor a 2 out. So that would become y is greater than 2 times the absolute value of x minus 1/2. So we're factoring a 2 out of that. When you factor 2 out of 2x, that is just x. When you factor 2 out of -1, that would be -1/2. So put the 2 on the outside so that you can see the slope of the right branch. Now this has a vertex of 1/2, 0. So the vertex is 1/2, 0. Slope of the right branch is 2. That's going to create the boundary line. Once again, vertex is 1/2, 0. And slope of the right branch is 2. So to graph that, put a point at 1/2, 0. That is the vertex. Now the slope of the right branch is 2. So from that point at 1/2, 0, go up 2 into the right 1, put another point. Slope of the left branch would be -2. So you could go up 2 into the left 1 and put a point there. Those 3 points make your V-shaped graph. Now it's a dashed boundary line because of that greater than sign, and it's shaded above also because of that greater than sign. So with the greater than sign, it's a dashed boundary line shaded above. But we should be putting these one right on top of the other because we're solving that system. So where these two overlap, that creates the solution set to this system. And that's what we're looking at right here. The bottom of this V right here, where that line intersects it, everything below that down to the vertex, that is the solution set to that system. So you pick any point in this overlap right here where that arrow is pointing, any coordinates, put those in for x and y. Those will make true statements in both inequalities because those points in that overlap are the points that those two inequalities share. So that is the solution to that system. That is the solution set right there. All of those points would be solutions to both inequalities. You get down here in the purple, those only work in one inequality, the top inequality. You get up here above this dashed boundary line right here, in this area, those are solutions to the absolute value inequality, but not the linear inequality. So what we're looking for here, the solution set, is the set of points that these two inequalities share, and it's right there where the red arrow is pointing. That is the solution set to that system. Which of the following graph shows the solution of the system in inequalities? Y is greater than or equal to -2x plus 2, and y is less than or equal to the absolute value of 3x. Well, the first thing that should catch your eye here are those inequality signs and what they would mean in terms of a dashed and solid line. Greater than or equal to, less than or equal to, that means we're going to be putting solid lines down. So anything with a dashed line is thrown out. So the F and the H, those have dashed lines making up those graphs, and those are now out of the picture. Anything with a dashed line is out because we have a greater than or equal to, less than or equal to. If we had a dashed line, it would just be greater than or just less than. So we're down to G or I. Now, the V-shaped graph, the absolute value graph, y is less than or equal to the absolute value of 3x, We can get that in vertex form or standard form by factoring a 3 out. If you bring a 3 out in front of the absolute value sign, then you can pick out the vertex and the slope of the right branch. So with that, y is less than or equal to 3 times the absolute value of x. The vertex on that would be at 0, 0. And then the slope of the right branch would be at 3. So with the vertex being at 0, 0, and the slope of the right branch being 3, the answer to this is definitely G.